of the precision is almost 0.05 nanometer precisions to assemble themselves. So that's why I inspired by those guys that do research about this thing. They can say that biology is the most powerful technology in the platform. And also here, this. If you know, do you guys know after the rain, there is a smell?
Yes.
So it's a volatile compound. So it's called, you know what is the compound name called? Geosmin. Yes, that's correct. So the name of the volatile compound is geosmin. Geosmin. And turns out that geosmin smell is produced by these words. Only 4 words, ATGC, and it's produced by this small bacteria. It's called actinobacteria that reside on the land. It's the credit frame.
Sorry.
Oh. So this bacteria consists of this DNA or this gene, and once it activated by the rain, it will be volatile, and we can smell the so-called good smell of the rain, right?
But like it's common bacteria on the ground, right? You can just get it.
It's not. You can say it's a common bacteria, but it's. I can say it's. There is lots of this kind of bacteria in soil. So it's actinobacteria, not only bacteria. It's subgenus of the bacteria.
Okay.
Okay. So if you can Google actinobacteria, ACTEINO bacteria.
And it's activated because of the rain or just any water?
So naturally they produce, and once they not activated, it's like having a chemical reactions with water, then it will be evaporated. Then this volatile compound, we can smell it, right? Okay, so the questions coming back for how come this bacteria able to express these words to become the smell. So biology has some sort of analogical and similar way. It's easier to take the depictions of analogical computation. We have MacBook, we have software, right? So to deliver the program, to do some stuff in the computer, we need the software. And also in biological process, we have the gene as the software, and also we have the living cells. For example, this kind is fungi. Then I come up with a question: what is possibly biological system can do and interact with? So what is the interactions between this? For example, this is my own project. I did this in Taiwan, in my supervisor lab, Glenn Charles lab. So this is just a simple staining for mycelia, for fungi. And then I try to use different kind of filter to see whether you can see if using the green filter, we can see something here. But when we use the red filter, there is nothing there. So we try to pinpoint which locations of the expression inside of our fungus. But what I would like to mention here is these are not only biology. We use optical also, like wave. We use optical to capture these images, and also we use chemicals. So biology is not erected only one single field, but also having some help from other fields, right? Okay. Another works. This is one of the research that I did in Singapore. They use different protein structures. This is my professor specialty. They use different protein nanocage as carriers for biomedical applications. For example, one protein called ferritin that produced by Archaeoglobus fulcidus for a factor or a vehicle to insert something, for example, let's say biomedical compound, to send and deliver to skin, for example, for skin patches or for any other therapies. And I also work with this. I work with E2 protein produced by Geobacillus steatothermophilus.
So Italian, so I think.
Yeah, but imagine what I would like to mention again about this. This is not only biological things, but we also discuss about structure, and these structures also have different purpose and applications. For example, one of my colleagues from France using this protein to coat the PCB, like electronical
PCB.
surface. Yeah, electronical surface, and then they coat the protein on top of the surface of the electronics. So they call it bioelectronic projects. So this is not only biological projects. Again, this one, the recent one that I've been hired in Singapore, we do PET or polyethylene terephthalate bio-upcycling. So we would like to, as we know that the PET problems, the plastic waste problems, we need to degrade them more efficient and so on and so on. Our labs, my professor project, would like to having a good and efficient system to degrade them, but not only to degrade them by using engineered enzyme. We would also would like to have bio-upcycling. So PET able to be degraded to become its monomer. For example, TPA or the terephthalic acid and also ethylene glycol. And these monomers able to be used by the next microbes, for example. And then what should they do? They can also make another virgin PET or another recycled products. So this is what we do in Singapore. And these are my recent projects. Now I have projects, but still in the design phase. So the challenging plastic waste upcycling from 368 metric tons, only like 83%, only 10% that has been recycled. And this project I proposed when I did the course of how to grow almost anything this year. This program is from MIT Media Lab, and I'm just simply inspired by the rotten fruit and vegetables. So if we leave the fruit and vegetables, it will easily degrade and also rot, right?
Yeah.
So why not we don't have a rotten plastic bottle? So what if we have this? Why not? Why not we have this? So these are just illustration, not yet the real project.
If it's like
Artificial intelligence.
Yeah, this one are the artificial intelligence. So I just type the keywords and then I would like to have the illustrations. And then, so these are my ideas. So I would like to have a products, quote unquote have a products called rotten, which are PET super degrading super fungal strain. So I would like to develop fungal strain that able to directly attach. So imagine we have bottles and then they can directly attach and then penetrate. They can directly use the PET substrate and use them as the carbon source for bioconversion or upcycling. So I divided this project into three different phases. The first phases will be the research and development for the fungi, and then the second one for the like verifications of the product, and then the third one is this burden of the rough sketch. So if I already able to develop the fungal strain, then I would like to have like simple waste bin. Like imagine we have just small simple waste bin, and then we have this fungal strain starter, and then we just like pour it down, and then they're able to degrade that kind of plastic. And then it can be used for industry or the recycling dump, or we can use also for personal consumer in home. So these thoughts I got from design thinking also, and these thoughts I discussed with one of the product designer, Elaine. So she was the teaching assistant of this course, and then I discussed a lot with her to get some more insight from product design perspective. So it's not only biological matter designs. So what I would like to mention is also, for example, in the problems of plastics, we are not only facing the biological limitations, but also material limitations. Because if you see that the plastic bottle, we see it's like just very simple, right? But turns out it's not. It has a high crystallinity, it has a low crystallinity, and then we need to optimize the enzymatic process to be able to degrade, and etc. etc. I don't want to go to the details, but that's the thing. Then after this, I just would like to mention some of the examples that we can learn together. That most of the biological system able to support your wildest ideas, or even something that perhaps intersect with arts also. For example, in these groups, they made wearable materials that embedded with cell-free system. So there is a system that are not using bacteria. So it's just like a powder. Once you get water, the system will be activated. And then with these ideas, they develop wearable materials like this. So for example, inside of the clothes, they patch some system inside, and then it can be a point of care personal, POC, point of care, right? Yeah. So that's why I like this example, because we are in the medical science department. I thought that we can discuss this with the students also. So these are the ideas that they bring. So again, this is not only biology, but also using material science, using technology, sensor, IoT, etc. And also within the same group, they also use this Sherlock. If most of the biology students know of CRISPR-Cas, they developed this Sherlock detection system to have a simple attachment in the mask exterior. So once we breathe, for example, let's say we are positive, COVID positive, then they will detect this, our titer of virus. So if it's positive, then we directly know that we are still infected by the COVID virus. So these are examples. Again, so that's for sensors. Now we also have materials, and I love this kind of stories because they name it engineered living materials. So somehow the living material able to self-healing, to self-assembly also. For example, they have this mycel leather, and then when they disturb and destroy a pit to make a circle like this, in the meantime they will heal by themselves. So for example, these are steps that related to the fungi growth. For example, here after they disturb the material, there will be grow chlamydospore, and then start to germinate, start to make another new cells inside, and then they will have healed materials. And also this one. So guess what is this one?
Try, yeah.
Cat.
What is that? Chocolate.
chocolate.
No.
No chocolate.
Yeah. So this box,
是粪便哦。
粪便。
yeah. So these box are poop.
Yeah.
And these
Yeah.
book are literally changed my perspective of how we use our daily life to what can we do within our daily stuff. So guys from UK IGM team developed the biosensor inside of the yogurt, and when we took that yogurt, and then if there's something happen within inside of our gut, we can detect directly in our poop. So we can do like a home care personal monitoring. So if there's something happen within our poop, then we can just directly go to the physician. Another materials for self-healing, this is the same from the US groups. They also engineered self-healing, engineered of fungal bacterial biocomposite. And then they grow in a lignocellulosic feedstock. And this is from cyanobacteria, another bacteria. They able to develop bioconcrete and carbon capture. And also spider silk. They also made lots of material using spider silk. Yes. And Spider-Man is correct depictions of what they do within the spider silks now. And you can, you guys in this room probably most known of this, right?
It's mushroom.
This is mushroom, right? But can you imagine we can make shoes from mushroom?
Yeah.
Yes, and it's already available. The famous Adidas Stan Smith already made from the mycelia leather, and it's called mycelia leather, called produced by Bold Threads company in US, and they stuff are really good. Even Stella McCartney, I already discussed one time with Celine. Then they able to make the world first garments created from the mushroom leathers. So these are not only biology. Biology able to give raw stuff, and then what should we do with the raw stuff, right? And then another intersections with the art probably. This is one most epic example that I like the story also. So the title is Resurrecting the Sublime. From Christine Agapakis in US. So they try to isolate the DNA from the old herbarium plant. So there is a story in the early colonizations of US because they bring sheep, right? And then sheep roam around and then eat some plants. And then because of this colonization process, one species that luckily already collected in the herbarium, it's extinct, like literally gone now. Then this group tried to isolate the DNA from the old herbarium and then plant it to yeast and then try to produce them, and then they make an exhibitions of the scent, of the smell of the lost or extinct plant. And then they make this kind of exhibitions of people can go and then smell the lost or extinct plant. So again, using technology, we are not only able to touch our daily life but also art sections. And last couple slides, I also have good examples that from this paper. There's a German scientist called Vera Meyer. This is, I already told Chai Chai that there is specific interactions between, for example, human to human and then also human to environment. But this is also happen with fungi. So, for example, if fungi here at Aspergillus niger, for example, in your plate, let's say,
Yeah.
if
the black mold.
yeah, I would say you put agar, sugar, and beef broth, right? So all of them are their source of nutrition, right?
Yes.
And then Perhaps in the early stage they will grow only white, but once the sugar are consumed and everything is depleted, they will become black usually in manga. It means that the environment already becomes stressed, so they have to preserve everything that they got, and they produce pigments. So that's why here they try to make an art project to understand that Aspergillus niger, when produce pigments, is also a response of something.
So it can be like a sensor in some sense.
Yes, in some sense like sensors, but also what can I expressing the pigments because of the stress related conditions. Or if we give another, how can I say it? Oh, it's more physical. Let's say I'm happy, I eat more,
I see.
I will be fat, let's say. But my work loads very hard, and then I feel tired. I never take a lunch or I never eat. I will be small again. So this is stress related, right? So in this kind of project, you can try to Google Vera Meyer color of life and this YouTube link, then you can see and try to understand more. So in the end, all of them are intersections of all aspect or nature. For example, computational design, manufacturing, material engineering, synthetic biology, and also artists. Then I just would like to encourage us, including me, that I would like to know you guys also as artists, and I welcome if I can be able to help in technical things in biology. So I believe that there is something that we can do together.
Come on.
And then last examples. This is like founding father of synthetic biology. Actually, I would like to mention this when Pak Boom's here because he is Pak Boom's PhD supervisor in Stanford, and both of them pioneering these fields are not coming even from biology. So they come from civil engineering and computer science before they use biology as their inspiration, as their way to learn about nature. So in the end, my reflections to myself is I would like to use nature not only as a technology, but also how it related to society. Not only we use them as technology to solve problems, but also how do we give back to nature, like intimacy with nature, right? Your previous workshop dance. So this is kind of my reflections. In the end, so cells can make copy of themselves, can contain biological machinery to put out many complex texts. Synthetic biology and biotechnology has the potential to produce eco-friendly solution, and it is also approach to learn about working with the natural systems. And this is just, I would like to mention about the balance between the food shortage, waste treatment, and etc. Because there's lots of problems in our daily life. That's why back to my title, finding interesting interest through interdisciplinary perspective. So it's not only from biological perspective. I can skip this, but last but not least, why innovate with biology? Because you can eat software. Open cup.
Yay!